So, we are back, and this time let us talk about different types of orbit and different types of initial condition that will lead to different types of orbit. Now, first consider the situation. We have let us say this is our earth surface, and we want to fire a rocket. So, this is my radius of earth, which is r0, and some point on earth, okay, we are firing a rocket at a velocity v with an angle alpha with the horizontal direction. Now, in this chapter and in this discussion, what we are going to do is we will try to find different conditions on this v and alpha. Okay. So, we will check out for different conditions of v and alpha, which will lead to different types of orbit, namely the circular orbit, the parabolic orbit, elliptical orbit and hyperbolic orbit. Now, all this will be discussed in terms of this eccentricity expression, which is given by 1 plus 2 E L square by m k square, right. Now, E, as we have discussed just now, can be replaced by half m v square minus v e square, right. So, eccentricity can effectively be written as root over 1 plus L square by k square v square minus v e square, right. So, now let us consider this particular case. We have to find, and so we somehow need to replace this k and L, which are present in this expression, with the parameters v and alpha and escape velocity v e. Now, it turned out it is not very difficult, as we can write expressions for L, the angular momentum, in terms of this two parameters. So, I am just calculating L here. L is by definition is r cross p. Here r is given by r0. Let us say this is my r0 vector, okay, and my p is m times v, okay. So, m and v vector. So, r0 cross v is m v. So, the magnitude, so this is my vector L, and my magnitude L will be sin alpha, and we are only interested in this magnitude here. Similarly, k can be replaced by the expression half m v e square is equal to minus v of r0, okay, which is given by k by r0, k being the force constant, right. Now, actually k, we know that k is equal to gm, but gmm, but we are not writing it in the explicit form. Now, once we do that, and now once we so we using this expression, we can write k is equal to m r0 v e square divided by 2. So, we have one value for L, one value for k, both in terms of the known parameters are 0, m being the mass of this particle, and v, ve and v. Now, we substitute this back into the equation here, and we can write the expression for eccentricity as 1 plus, so it will be m square v square r0 square sin square alpha divided by m square. So, there will be 2 will go up as 4. So, it will be m square r0 square Ve to the power 4, and we have V square minus Ve square, right. Now, this 2 cancels, this 2 cancels, leaving behind, and then what we can do is there is a V square here and V to the power 4 here, and so we can take V square from it inside this bracket, and we can write this whole thing as 1 plus 4 V by Ve whole square, into 1 minus, we can write this as 1 plus 4 times V by Ve whole square into V by Ve whole square minus 1, right. Now, this can be further simplified to give epsilon is equal to root over 1 minus 4 c square into c square minus 1. Oh, sorry, totally missed. There is a sin square alpha term here. So, it will come here in the final expression. So, we get an expression for epsilon, which is root over 1 minus 4 c square sin square alpha c square minus 1, and where c is equal to V by Ve, right. So, we got everything in terms of the known parameters. See, V by Ve, Ve is something that we typically we know or we can calculate easily. V is the velocity of initial velocity of the mass, projected mass, which is also known to us. So, that way C is known, alpha is the angle, and that is all we need. So, you see, essentially we started off with an expression of epsilon, which was of this particular form, and that we in one of the previous classes we proved, we got this expression by using 2 differential equations we got for central orbit, for one inverse square law of force, okay, or rather we used the equation of conic section L by R equal to 1 plus epsilon cos theta, and 2 sets of differential equation, and essentially got this expression in terms of energy, angular momentum and force constant. Now, this entire thing can be reduced to this simple looking expression, which is in terms of the velocity of projection, not even the mass of the object comes into the picture. So, it is all in terms of velocity of projection, the escape velocity from Earth's surface and the angle of projection. It is an amazing transformation. it is a very simple equation, but it is that this entire transformation is amazing, because how simplified things can be if we just if we are smart enough. And this is the starting point of the this is the master equation, I would say, if we want to determine the shape of the orbit for a given value of alpha and c. Now, let us first look into the condition for circular orbit, because we have already discussed circular orbit many times, and every time I have discussed circular orbit, I told you that circular orbit is a special case of elliptical orbit, and there are certain conditions that has to be satisfied in order to get a circular orbit. Now, we are going to show you, I am going to show you what are these conditions which has to be satisfied in order to get a circular orbit for an artificial satellite. So, here we are considering the cases which is typically the cases where mass is projected from Earth's surface towards outer space. It could be a satellite, it could be a missile, it could be a rocket, and we are trying to see what will be the nature of the orbit. But this particular analysis is equally valid if we want to look into the, if we want to calculate the trajectory for different heavenly bodies, for example a comet, a shooting star. But of course equations, these are simplified equations. We are not taking into account the air resistance, not taking into account any other nonlinear effect that might be present in the atmosphere. We are not taking into account any of the attractions that can be exerted by any other heavenly bodies. So it is a simplified model, but it is a very effective model. So the equation, as I said, again I am repeating myself once again, the same set of equation can be used to determine the trajectory of a shooting star or a comet as well. Only thing is we need to have a very good idea of the escape velocity or the set of initial condition which describes the initial velocity, the escape velocity at that particular point, and the launch angle at which it was launched, right. Now let us come back to this circular orbit. Circular orbits is defined with epsilon equal to 0. Now if epsilon is equal to 0, then we see that from this expression 1 minus 4 c square sin square alpha c square minus 1 equal to 0, or which gives 1 minus 4 c to the power 4 sin square alpha plus 4 c square sin square alpha. We can put equal to 0 here, but we are not doing that. What we are going to do is we are going to add 4 c to the power 4 sin to the power 4 alpha minus, again we subtract the same quantity. So it is just a mathematical manipulation to bring it to a particular shape. Now let us look at this. If we take this term and this term, okay, if we take this together, these three terms will give us 1 minus 4, or rather sorry, it will give us 1 minus 2 c square sin square alpha whole square, or 2 c square sin square alpha minus 1 whole square, does not matter really. And the other two terms in the expression, if we pair them up and take 4 c square sin square alpha common, or actually we can take them to the other side. So if we do that, we get this sin square alpha, so it will give us sin square alpha minus 1, right. So now focus on this expression. So on one side we have 1 minus 2 c square sin square alpha whole square, and the other side we have 4 c square sin square alpha into sin square alpha minus 1. Now the left hand side is positive definite because it is a square of some term, okay. So LHS is a positive definite. RHS is generally negative, right, because sin square alpha is never greater than 1. So sin square alpha minus 1 is equal to negative all the time, except when we have alpha equal to pi by 2, then my right hand side becomes 0. So it can have or I should not say positive definite, it can be positive definite or 0. So it can be either positive or 0, and right hand side can only have a 0 value at alpha equal to pi by 2. For any other alpha which is less than pi by 2 or greater than pi by 2, we can have this side as negative. The only time these two sides can match is for this particular value of alpha, okay. So this is the condition which has to be met in order to satisfy this equation to be satisfied. Now if this is equal to 0, then we have from the left hand side we have 1 minus 2 c square sin square alpha is equal to 0, which gives c equal to 1 by, or and we have to put sin, so we have to put the value of sin square alpha, so it will be 1 minus 2 c square. So if we put alpha equal to pi by 2, sin square alpha is equal to 1 equal to, so 1 minus 2 c square equal to 0, which gives c equal to 1 over root 2. Okay. So this is another condition. Okay. So we see that the condition for circular orbit by looking at this calculation is alpha equal to pi by 2, c equal to c, which is equal to v by ve is equal to 1 by root 2, right. So if and only if this condition is met, we can have a circular orbit. Any other, no other initial condition will give us a circular orbit, right. Okay. So now we know, and also we can calculate the total energy of a circular orbit, and we can show immediately that total energy E of a circular orbit is given by half V of R0. Okay. So I am just leaving this to prove up to you for as an exercise to prove. It's very easy. If we start from the consideration once again, I mean initial values once again, this is very easy, right. Now let us go into the more general case of an elliptical orbit. Now elliptical orbit epsilon we know has to be between 0 and 1, right. Now once again we look into the expression for epsilon, which is given by 1 minus 4 c square sin square alpha into 1. So you can either have a plus and write c square minus 1, or you can write 1 minus c square, the way whichever way you prefer. For this particular case it's easy, I mean it's better visualized if we write minus and 1 minus c square. So that's why I am doing it. Otherwise previously we can also write c square minus 1 and we can put a plus sign here, right. Now if this is the case, we can, and we have already seen that for v equal to v equal to ve by root 2 and alpha equal to pi by 2, we can get a circular orbit. Now the elliptical orbit can be achieved either for a velocity v which stays between ve by root 2 to ve, okay, or we can also get an elliptical orbit for velocity v which is greater than 0 and between ve by root 2. Why I am classifying these two ranges specifically, we will see towards the end. We will see why it is important to have this. Okay. Also we can have an elliptical orbit if we have v equal to ve by root 2, but alpha is not equal to pi by 2. If alpha is equal to pi by 2, we get a circular orbit. If this is the case, the velocity remains same, but we do not have a vertical launch. So alpha equal to pi by 2 essentially means, if you recall this picture, alpha has to be equal to, alpha equal to pi by 2 means this. So it has to be launched horizontally, right. So this is the condition for a circular orbit. Now if this condition is not met for any other alpha, which even if our velocity condition is met for a circular orbit, but our angle condition is not met, we can also have an elliptical orbit. So essentially these are the three domains in which we can have elliptical orbit, right. Now, inside elliptical orbit we can have two broad classifications. One is a satellite and one is a ballistic missile. Okay. How to define, how to distinguish between these two? Let us say this is my Earth surface. It is given, the radius is given by r0, and I am launching an object from this particular point with some velocity v and angle alpha, right. And let us say this velocity v is less than ve, so we will get an elliptical orbit. Now, if the condition is such that, that this particle can continue on this elliptical path, so that, okay, so it will be a what you call, it's a ellipse with, because it's the gravitational pull coming from Earth's surface. So, Earth's surface has to be in one of the focus of this particular ellipse, right. Now, if Earth has to be in one of the focus, the shortest distance is this distance, which is given by the length of semi minor axis B. If your shortest of R is greater than B, only then it can continue on this orbit and we have a satellite. But on the other hand, if we have a situation where after launch this condition is not met and it hits, I mean, your length of this semi minor axis is not greater than the shortest distance r0, which is the shortest possible approach to this to the Earth's surface, okay, then what happens is it will come back and hit the Earth's surface at some point, right. So, in this case we have a ballistic missile. So, we have one case where r is, or B is greater than r0, or sorry, capital R0, that is the case of a satellite, or I will just write it there maybe, yeah. So, this is the case when B is greater than r0, and this is the case when B is less than r0. So, we are, why r0? Because r0 is the shortest possible approach to the force center, which is in principle allowed. Of course, we have to give it a relaxation. A satellite cannot pass, pass very close to the Earth's surface. There has to be a certain gap here, which for the calculation sake we are ignoring, and we are assuming if B is greater than r0, then it is a satellite, and B is less than r0 is. So, in principle there has to be a minimum gap, which is r0 plus h and r0 minus h. Okay. Now, let us look into the calculations. So, for first we have to set the condition B greater than r0. Now, what is B? If you recall, B is equal to A root over 1 minus epsilon square, and A was given by L into 1 minus epsilon square. Okay. So, in terms of L, B is equal to L root over, or sorry, L divided by root over 1 minus epsilon square, right. Now, if we substitute the values for L and epsilon, we see it is L square by m k divided by L by k root over V e square minus V square. So, we just have to go back to the definition of epsilon and substitute this here. If we do that, and if we do this reduction at the end, so this will cancel out, this k will cancel out. Okay. So, if we do all this, perform all this calculation, So essentially we will be left with C R0 sin alpha into C R0 sin alpha root over 1 plus or 1 minus c square. Okay. So this is your B. Now if B is this, then B by R0 is equal to C sin alpha into 1 minus c square. So here I did not show the calculation. All you need to do, you need to substitute the again you are initially launching at a velocity v and with an angle alpha. So you have to substitute L equal to m v r0 sin alpha into this expression, and you have to write C equal to v by ve. You immediately get this expression that V is equal to C R0 sin alpha into 1 minus c square, right. So for satellite, as I have discussed already, this ratio has to be greater than 1. So we have C sin alpha greater than root over 1 minus c square, and which essentially gives C square sin square alpha greater than 1 minus c square. Simplifying, we get an expression C greater than 1 by 1 plus sin square alpha whole root. Fine. So range of sin square alpha is now between 0 and 1. Okay. So the highest we can have in C is the highest of C can be equal to 1, and the lowest of C can be C equal to 1 by root 2. So we see velocity has to be enclosed between VE by root 2 to VE in order to have a satellite. C equal to 1 essentially means V is equal to VE. C equal to 1 by root 2 essentially means V is equal to VE by root 2. So that defines, so range in sin square alpha, because alpha can have range between 0, sin square alpha can have range between 0 and 1, it defines the range as V to V by root 2. So if this condition is met, we have the condition. If this particular condition is met, then we have a satellite. And if this ratio, if we go back here and set this ratio less than 1, we will find out similarly we will find out a range of V which is given by this. And for this particular case, as I have discussed already, as the length of semi-minor axis is less than r0, the object which will be projected from Earth will come back and hit the Earth's surface at some point. And this particular case, as we have discussed, is called the ballistic missile. So we see that we have two cases, as we have, why we have specified this, because in this particular case we can have a satellite. Also we put a equal sign here because of we consider this as a special case of this one. So if we have a velocity condition which is between escape velocity and escape velocity by root 2, then we can have a satellite. So the object will end up going into the outer space and into an orbit around Sun, around Earth, and if this is the case, then it will come back and we have a missile. Okay. So with this we end today's class. Next class we will take up some problems on this, and also there are different other types of orbit where situations like parabolic orbit and hyperbolic orbit, which will be discussed briefly, and then of course we will do some problem, and then we will move on to the next topic from central forces. Thank you.